Hello, welcome to this new lecture of the course Transportation Network Analysis. So, in the last class, we had seen the first order conditions for the optimization formulation of user equilibrium, which is the Beckmann's transformation. So, from there, we are continuing again. So, there are two kind of paths which are connecting any OD pair RS. First, that do not carry any flow. So, their travel time is greater than or equal to the minimum OD travel time. So, if you remember in the equivalency conditions that we saw, there was this CKRS, which is the travel time on path K connecting R to S. So, if there is a path where the flow is 0, so then the only important condition that we have is CKRS is greater than or equal to URS. Okay. So, this was the second condition. The first one was FKRS times CKRS minus URS is equal to 0 for all K, R and S, okay, and this condition holds for all again K, R and S, okay. And then we had additional constraints 3 and 4, which are the regular constraints of the optimization formulation. So, I am not writing down here. So, if FKRS is 0, that is this is 0. So, then there is no important information that comes from this equation, and the only thing that we get is CKRS is greater than or equal to URS. For the case when FKRS is equal to FKRS is positive, that is the path K connecting R to S carries flow. So, if this is positive FKRS, so then CKRS has to be equal to URS. Okay. So, that is what it is saying, that the travel time is equal to the minimum OD travel time. Okay. So, for each OD pair at user equilibrium, the travel time on all used paths is equal and is less than or equal to the travel time on any unused path. Okay. So, this definition we have seen before also. So, therefore, the first order conditions of the Beckmann's transformation or the optimization formulation for user equilibrium are equivalent to the user equilibrium conditions. Okay. That is why they are called equivalency conditions. Now, note that the solution of the first order conditions is a stationary point. Okay. So, it need not be the optimum or the minimum point. So, that is why we require additional conditions to argue that. So, the following conditions are used to argue that the obtained solution x star is a unique minimum. First is that the objective function is strictly convex in the vicinity of x star, then objective function is convex everywhere and the feasible region is convex. Okay. So, we have seen these conditions before also. So, we have seen what does an function being convex or strictly convex means and what does a feasible region being convex means. So, let us first focus on this last condition. Okay. So, what we want to do here is that we want to argue that the optimization formulation of user equilibrium, that is the Beckmann's transformation, satisfies some conditions so that this holds. Okay. And if this will hold, then whatever solution we obtain from the equivalency condition that we saw, so those solution is a stationary point and that will also be the minimum point, okay, or the optimum point. So, let us first argue that the feasible region is convex in Beckmann's transformation. Okay. So, a region is said to be convex if a line segment connecting any two points of each region lies entirely within the region. Okay. So, we have seen this definition of convex region before also. Now, for the optimization formulation of user equilibrium, that is Beckmann's transformation, the constraints are linear, if you recall, and therefore, the feasible region is convex. Okay. So, if you do not remember the constraints of this Beckmann's transformation, I will just quickly write. So, we have the first constraint as summation FKRS is equal to QRS for all RS, then FKRS has to be greater than or equal to 0 for all KR and S, and then we have this thing that XA is equal to this FKRS times delta AKRS, okay, and this holds for every link A. So, all of these constraints are linear, okay. This one you can see directly is linear, this is also linear, and this is also linear because delta AKRS is given, because this can be obtained from the network structure. So, these values are known, and that is why this last constraint is also linear. And when the constraints are linear, the feasible region is convex, okay, because then we get something like this, that an example of a region which is obtained from linear constraints can be something like this here, okay. So, for example, this is first constraint, this is second constraint, this is third constraint here, this is fourth and fifth. So, this feasible region would be obtained from the intersection of these 5 conditions, that for example, we would want that we need to be on this side of this constraint 1. Similarly, we need to be on this side of the constraint 2, and so on. So, when we are looking at the intersection of all of these conditions, we will be getting this polygon that we have here, okay. So, this is convex because if you pick any 2 pair of points here and you join them by a line segment, then this line segment will lie entirely within this region, okay. Okay, so the feasible region in Beckmann's transformation is convex because we have the linear constraints. So, these are the constraints that I mentioned, okay. Okay. So, now let us argue that the first 2 conditions that we saw, that the feasible region, that the objective function will be strictly convex at any point x star and the objective function is convex everywhere. So, let us argue that these conditions also hold for this Beckmann's transformation. So, the following assumptions on the link performance functions ensure that the objective function is strictly convex in the vicinity of x star and convex everywhere. First is that we are assuming that the travel time on a given link is a function of the flow on that link only. Mathematically, what it means is that if you take the partial derivative of this travel time function Ta with respect to the flow on link B, then that will be equal to 0 if A and B are not the same link, okay. So, one might think that this is a very obvious assumption, that why should the travel time on a given link be a function of the flow on other link. The situations where this assumption may not hold is, for example, if you have a road and it has 2 directions. So, suppose in the 2 directions there is no divider in between these 2 directions, and in that case sometimes the vehicles which are flowing in one direction can go into the space for the other direction while they are overtaking and so on. So, in those situations it can happen that the flow on one direction can influence the travel time on the other direction. So, we can consider that these 2 directions are kind of 2 links because they have different directions, and in those situations this assumption will not hold. But let us assume that the situations that we are considering make this assumption, and we also assume that the link performance functions have positive slope, this, okay. So, with these 2 conditions, we will be arguing that the objective function will be strictly convex at x star and it is convex everywhere, okay. So, in order to argue about strictly convexity and convexity of the objective function, let us recall what the objective function is. So, this is the objective function in the user equilibrium formulation. So, in order to argue that this function is strictly convex at a point x star, we need to determine the Hessian of this objective function and need to argue that it is positive definite at the point x star that we are concerned. So, this Hessian matrix is the matrix of the second derivatives of this function zx with respect to x. So, the derivative of this zx with respect to the flow on the mth link is then given by this, okay. So, if this is zx and if you take the partial derivative of this with respect to the flow on the mth link, this is what you will be getting, and this is coming from the fundamental theorem of calculus. So it is assumed that many of you would have seen this uh, theorem of calculus before. If not, I'll say is that you revisit this fundamental theorem of calculus. Okay. So since we have to calculate the second derivatives of zx, so that's why first we are determining the first derivatives, and then we will be again differentiating them. Okay. So therefore, the derivative of this with respect to the flow on the nth link is equal to. So now we are determining the second derivatives. So if we are taking the derivative of Tm xm with respect to the flow on xn, now if m and n are different links, then this will be equal to 0. And why this is coming? Because of the condition that the travel time on link k is only the function of the flow through that link, and if we take the derivative of that function with respect to the flow on any other link, then this will be equal to 0. Okay. But if we are taking the derivative with respect to the same link, then this is what we get. Okay, this is the slope of the travel time function, okay, at the given point. So now we are ready to determine this Hessian matrix, because we have determined what do the second order derivatives look like. So this now means that all the off diagonal elements of the Hessian matrix are 0, and all the diagonal elements are given by this. That is, the Hessian matrix is given like this. Why? Because we have these zeros at all the off diagonal places, and we have these terms, the slopes, at the diagonal places. Okay. Now what can we say about this matrix here? So we want to argue that this matrix is positive definite. So this matrix is positive definite as it is a diagonal matrix that has strictly positive entries, because these values, the derivative of the travel time functions is positive, because this is the assumption that we made. So we have been dealing with travel time functions of this form from the beginning, if you recall. This is TA and this is XA. Okay, so we are assuming that the slope is always positive. So therefore the objective function is strictly convex everywhere, and since the feasible region is convex as well, the UE program is having a unique minimum. Okay. So we had already argued that the feasible region is convex, and now this Hessian matrix that we saw, that is positive definite at all the points. Okay. So we had not argued that this matrix is positive definite at a particular point, but it is actually positive definite at all the points. So therefore this objective function is strictly convex everywhere. Okay. So therefore if the objective function is strictly convex everywhere, it is also strictly convex at a given point x star, and it is also convex everywhere. Okay. Therefore those two first conditions also hold, and the feasible region is convex, and therefore the Euler-Equilibrium problem has a unique minimum. So whatever solutions that are obtained from the first order conditions, those are also the minimum. Okay. Now one thing to note here is that the Euler-Equilibrium solution that is obtained is unique with respect to the link flows, but may not be unique with respect to the path flows. Okay. So all of this second derivatives and so on that we have taken while determining that the objective function is strictly convex or not, those are with respect to the link flows. Okay. And it just so happens that this uniqueness of the solution is with respect to link flows only, and there can be multiple solutions that have different path flows for a single solution of link flows. So let us see an example for that. Suppose we are considering this example where we have 4 links. Okay. So the travel time functions are shown here, and it is given that the demand from origin A to destination D is 2 units, and the demand from origin B to destination D is 3 units. Okay. Now we have seen this kind of network before also. So here there are 2 paths for every origin and destination. Okay. Now suppose we have to determine what is the Euler-Equilibrium solution. Okay. Now, how to determine that? So, note that all the flow that takes place from origin A to destination D has to pass through link 1. Okay. And since the total demand from A to D is 2 units here, so x1 has to be equal to 2. Okay. Similarly, since all the flow from B to D takes place through this link BC here, and since the total demand from B to D is 3 units, therefore x2 is equal to 3. Okay. So, we have already obtained what x1 and x2 will be in the equilibrium case. Now, we need to determine what x3 and x4 will be. Now, one thing we know is that x3 plus x4 will be equal to the total demand that flows through both the origin destination pairs. So, this will be equal to 2 plus 3, because once we reach the node C, all of the demand, which either it is originating from A or to D, is traveling between C to D. So, whatever the flow is on link 3 plus the flow on link 4 has to be equal to the total demand. So, one equation that we get is x3 plus x4 is equal to 5, and the other equation that we have is that the travel time on link 3 will have to be equal to the travel time on link 4. Why is that the case? Because suppose if we assume that if the first OD pair is suppose AD, and let us assume that both the paths that are connecting A to D have positive flow. So, then the travel time on both the paths have to be equal. Now, this link AC is common in both the paths that are connecting A to D. So, then the only option that is left is that the travel time on link 3 will have to be equal to the travel time on link 4. And similarly, if you follow this next OD pair BD, then also it will come out that the travel time on link 3 has to be equal to the travel time on link 4. Okay, so this is another equation that you will be getting. Okay, so once you solve these two equations, you will be getting x3 is equal to 3 and x4 is equal to 2. Okay, so now we have determined what are the link flows in the user equilibrium solution. So, this is the only solution that we get. Okay, but there are multiple path equilibrium solutions, that is there can be multiple path sets, so that they will result into the same link flows. Okay, so the two of those solutions are shown here, but there are actually many more. So, one such set of path flows is this. Suppose 0 flow takes place from A to D on the first path, 2 units of flow take place on the second path connecting A to D, okay, and then 3 units take place on the first path connecting B to D, and 0 unit flow from the second path connecting B to D. Now, let us see how do these path flows result into this. So, if 0 flow is taking place with the first path connecting A to D and 2 units is flowing on the second path connecting A to D, so then the total flow that is taking place through the first link will be equal to F1 AD plus F2 AD, and this will be equal to 0 plus 2 equal to 2, and this matches with this thing here. Okay. Similarly, x3 will be equal to the flow on the first path connecting B to D plus flow on the second path connecting B to D. So, this will be equal to 3 plus 0 equal to 3. Okay. Let us see what is the flow on x3 from these path flows. So, x3 will be equal to what? The flow on the first path connecting A to D plus the flow on the first path connecting B to D. Okay, so this is equal to 0 plus 3 equal to 3. So, again this matches here. Okay, what is the flow on the fourth link here? So, this is equal to flow on the second path connecting A to D plus flow on the second path connecting B to D. So, that is equal to 2 plus 0 equal to 2. Again this matches. Okay. So, this set of path flows results into these link flows. But then this is not the only set of path flows which will result into these link flows. Another such set is this here. Again you can check. So, let us determine what will be the flow through link 1. So, that will be equal to F1AD plus F2AD. To 2 plus 0 is again 2. Then the flow through link 2 will be equal to F1BD plus F2BD. That will be 1 plus 2 equal to 3. Again it is matching here. Similarly, the flow through link 3 will be equal to what? It will be equal to the flow through the first path connecting A to D plus the flow through the first path connecting B to D. So, 2 plus 1 equal to 3. Again it matches. And then the flow through the fourth link will be equal to F2AD plus F2BD. So, 0 plus 2, again it matches to B2. So, in fact, there are multiple solutions which will result into the same link flows. Okay. So, this uniqueness of the solution is with respect to the link flows only and not the path flows. So, now that we have determined these first order equations or the equivalency conditions for the user equilibrium problem from the Beckmann's transformation. So, let us see that how those can be used to determine the user equilibrium solution. And why is that useful? Because until now the only way we knew to find the user equilibrium solution was to use a graphical method. Okay. And in that method it may not be easy to find the solution if the network is complex, because there we have to sometimes take a lot of cases. For example, we will have to assume that if there is a particular origin destination pair, then suppose these set of paths are the use path and suppose these are not the use paths. So, then we do some calculation and we have to make similar assumptions for other OD pairs also. But with this given set of assumptions, the solution might not be correct. So, then we will have to change our assumption. So, if we keep doing this, it can be very messy to determine the user equilibrium solution. So, that is why these first order conditions provide a systematic way of determining the solution of the user equilibrium. So, these are the first order conditions that we have here. So, since we have a single OD pair here and there are two paths connecting this origin destination and each path has a single link here. Okay. Now, that is why we are having these two equations here for this OD pair. So, this is saying the flow through the first path connecting O to D times the travel time in first path connecting O to D minus this OD specific Lagrange multiplier UOD. So, this is equal to 0. Okay. And similarly for the second path we write similar equation here. Then we have again these two equations because we have two paths connecting O to D. Then we have that the sum of the two paths here will be such that the flows sum to 0.5 and the path flows are non-negative. Okay. Now, we need to do one more thing before we can solve these equations. We need to substitute that the travel time on the first path connecting O to D will be what? It will be equal to the sum of the travel times on different links that contain in that path. Now, in this example, there is a single link 1 which is part of this path. So, therefore, C1 OD will be equal to just the travel time on the first path, which is equal to 2 plus x1 square. Similarly, the travel time on the second path connecting O to D will be 1 plus x2 square. Okay. And we also need to substitute that F1 OD is equal to x1. Similarly, F2 OD is equal to x2. Okay. That is, the flow on the first path connecting O to D is the same as the link flow on the first link, and the flow on the second path connecting O to D is equal to the link flow on the second link. Okay. So, once we do that, then we can obtain the solution. Now, I am not writing down the solution here because the same example we have covered before also. So I'll suggest that all the students actually solve this example by doing the substitution, and try to check whether they get the same solution that was obtained by the graphical method. Okay. So with this we'll be ending this lecture here. Thank you.